Good afternoon, everyone. It's my great pleasure to be here. I want to first thank Moro and other organizers for inviting me to join this wonderful workshop. Actually, this is my first on-site conference since the pandemic. So today I'm going to talk about nanoplasmonic thermal emission in near and far fields. I want to acknowledge 3 of my students who are involved in this work. So why do we need to study the nanoplasmonic thermal emitter? Nanoplasmonic emitter, such as nanoparticles, nanorods, nanowire, have a broad range of applications, for sensing, for energy conversion, because they are the fundamental building blocks for metamaterials and metal surfaces. So here we try to understand thermal emission, how much thermal emission we could extract from individual nanoplasmonic structures. For example, if I give you one nanoparticle of nanowire, we want to know, what's the maximum thermal energy we can have from those nanoplasmonic emitters, and with different geometry, with different material. Once we have a better understanding about the thermal emission from the nanoplasmonic structure, so we could further design and control the overall thermal emission from the metal material or metal surface consisting of those nanoplasmonic emitters. So let me first introduce the Quasi-Normal theory, which is the foundation of a theoretical framework for studying the thermal emission from nanoplasmonic emitter of any other resonant thermal emitters in our work. Physically, the Quasi-Normal modes are essentially the eigen solutions to South-Korean Maxwell equations in optical resonator, our optical cavity, our plasmonic resonator. But if we have a lossy resonator, for example, a plasmonic structure, we know it's lossy, the eigenvalue of the Maxwell equation, here is this eigenfrequency omega n, essentially is a complex number, so in which the real part is the oscillating frequency of this mode, whereas the imaginary part represents the quality factor on the lifetime of this corresponding mode. Mathematically, the orthonormality and the completeness of these Quasi-Normal modes are described by these 2 equations. So if you guys want to know more details about Quasi-Normal mode theory, please refer to this seminal paper published in the TIL in 2013. So the question is why those Quasi-Normal modes are useful for us. As we all know, usually we calculate the thermal radiation, no matter how far field or near field radiation, using the dyadic Green functions. Professor Zhou Minzhang already, discussed a lot about the dyadic Green function. So generally speaking, if we know the dyadic Green function, we know the material property, we can just calculate far field of near field thermal radiation. However, in many cases, because structure is so complex, it's very hard to obtain this Green function. Once we solve the Maxwell equation to obtain those Quasi-Normal modes, we can further expand the dyadic Green function based on the Quasi-Normal modes, as you can see from this equation. And then we can plug in back to these 2 equations and calculate the thermal radiation. So this is the general methodology, regarding how to calculate thermal radiation based on Quasi-Normal modes. Here I want to skip the lengthy mathematical derivation direct jump to the final results. So you can pay attention to this equation. You can see here, this is a radiative heat flux. It has included 3 major terms here. The first one is the Lorentz line shift function, because we consider resonant thermal emitter. This is well-known Planck terms. So we have this psi term here, can be expressed for far field and near field radiation based on these 2 equations. We specifically introduced 3 parameters, which represent the fractional mode losses here. The first one, as you guys can refer to this schematic, this is a general physical picture. So we have This is emitter, this is absorber. We have a near field interaction between these two. And also from this emitter, we have the profit radiation to the outside. So the first fractional mode loss factors is a resistive mode loss because the material is lossy, right? We have a mode loss inside of the material. So this is for emitter. Similarly, we can define the resistive mode loss for the absorber. And finally, we have this radiative fractional mode loss to the outside surrounding. Once we have these cardinal modes, we can fully express these three parameters, as you can see from the three equations here. And also we can introduce these imperfection factors due to the non-formation effect. So this is the entire theoretical framework. So basically we have, these two major equations, right? Because the rest is the same. Planck term and the Lorentz shape function are the same. So let's further take a look at these two equations. Generally speaking, we can use this one to predict the near field and far field thermal radiation. But more importantly, from these two equations, we can also know if we want to maximize or optimize structure to achieve the maximum thermal radiation, we have to match this mode losses here. For example, for the far field thermal radiation, we have these two parameters. One is represents the resistive mode loss inside of the emitter. The other one is a radiative mode loss to the outside surrounding. So if you match these two, so we can reach the upper limit of a theoretical limit we have for the far field radiation. Similarly, for the near field thermal radiation between two nanoplasmonic emitter, we can just match the resistive mode loss inside the emitter and also resistive mode loss inside the absorber. So in this case, we can achieve the maximum for both cases. So how large is this upper limit? As you can see from here, if we consider a single mode emitter, so the peak height actually just have a simple value is theta over 2 pi. So this one, as I mentioned, is a single mode. But certainly, if you have a complex geometry, you have a symmetry, you can have a multi-mode or degenerate mode. So we have another set of theory to deal with those problems. But here is just give you a simple example for the single mode, the nanoplasmonic emitter. I also want to mention, Professor Fan's group use a coupled mode theory, actually derived a very similar limits as this one. So this upper limit actually is very important because it tells us how much energy, thermal energy we can extract from a nanoplasmonic resonator. So how large it is, if you can do the calculation. So it's supposed to give you a nanorod of nanowire. So the thermal emission from this nanowire at a certain temperature can be 3 orders of magnitude larger than the black body radiation for the based on the physical area of this nanowire. Physically, this is understandable because we have subwavelength nanoplasmonic structure. So its emission cross-section can be much larger than its physical area. So that's why it can be 3 orders of magnitude larger than black body radiation. But in practice, it's very difficult to use individual plasmonic structures. We always pack those nanoplasmonic resonator as an array. So we create this metamaterial and meta surfaces for the meaningful applications. So here we have another question. Once we put them together, how the coupling between the adjacent nanoplasmonic emitters will affect the overall thermal emission from this meta surface. So roughly speaking, we can divide it into 2 regimes. The first one is a weak coupling regime. So this is also very understandable. It's like, if you have those nanowires, nanoparticles well separated, they don't really, interact with each other. There is a little crosstalk between them. So in this case, we can also imagine, so the thermal emission from the individual nanostructure will determine the overall thermal emission because they don't have a crosstalk. On the other hand, we have another regime. You have a strong coupling. So they have, the nanoparticles of nanowires will strongly interact with each other. So in this case, we have to quantify the coupling between them in order to determine the overall thermal emission from the metal surface. So regarding the weak coupling regime, we did a simple experiment. We designed this metal surface, use this plasmonic structure as the building block. So we can have different geometries here. And also from previous slides, we already have a quasi-normal mode theory to really optimize the thermal emission from this individual nanoplasmonic structure. Certainly we can do experiments, we can measure the thermal emission, but from theory we can also predict it. Our goal is to achieve this perfect thermal emission in this experiment. As you can see from this measure spectral emissivity, we do observe, the tunable thermal emission if you tune the geometry here. But at a certain geometry, you can achieve a maximum. So this one you can see is close to the perfect thermal emission. We have emissivity around 95%. And also this value is very consistent with our prediction from quasi-normal mode theory, as I mentioned in the previous slides. But another question is, if you have, if we pack those nanoplasmonic structures very densely, suppose we are getting into this strong coupling regime, so the physical picture becomes more complex. That's because the optimization of one individual nanostructure does not guarantee the global optimization from the metal surface. For example, physically, we cannot say the collective thermal emission from this metal surface is equal to the thermal emission from individual nanoplasmonic thermal emitter multiplied with the number of the thermal emitters inside this metal surface. Okay.
Equality because the strong coupling?
Yes, that's from coupling. We need to have a
In the weak coupling, you would have an equality, suppose.
So once you consider the coupling, the physical picture is more complex. In my next slide, I will show you what it looks like.
Okay.
We have a new set of theory to really explain the coupling and quantify the interaction between adjacent nanoplasmonic emitters.
Okay, thank you.
So how to solve, this problem and answer his question here? So let's take a look at this schematic here. When we form a metal surface, right? Certainly the physical picture becomes more complex. And, if you have just one plasmonic resonator, as I mentioned from the quasi-normal theory, we have the energy loss inside this plasmonic resonator, and also we have a radiation mode loss to the far field, right? But once we put other plasmonic resonator next to it, so we also have extra energy losses from this nanowire to the adjacent, the neighboring, the nanoplasmonic emitters. Okay, so you can also think about, when we consider this physical picture, we have one single emitter, and surrounding it, we have n nanoplasmonic emitters. Okay, and from the quasi-normal theory, we already derived this one to describe the radiative heat flux. So the question is, if we put them together to form a metal surface, so how to deal with the coupling? So here we introduce this effective number of emitters. So this NF actually is to count the coupling between adjacent nanoplasmonic emitters. And physically, you can also think about this parameter should be related to the packing density, right? How densely you pack it, and also the substrate you use to support this metal surface, and also the quasi-normal modes excited, from this plasmonic emitter. Okay. So this one again, you can see, we have this, quasi-normal modes. We can actually calculate this one. In this work, we also include the tight bonding model. So really, tight bonding model is for when we calculate the electronic band structure. So here we borrow a similar idea to calculate the coupling for this periodic, metal surface. Depends on the correlation of this parameter effective with packing density. We can observe three scaling behaviors here. So let me explain to you guys one by one. This is a general, formula we have here. We call it the skew law of far-field thermal emission from metal surface. So the first regime is uncoupled. As I mentioned, there's no crosstalk between two adjacent nanoplasmonic emitters. So in this case, the total thermal emission is linearly proportional to the total number of plasmonic emitters inside this metal surface. The second case is a so-called super radiance effect. So in this case, because the nanoplasmonic emitters coupled with each other so strongly, such that the total thermal emission actually inversely proportional to the number of the nanoplasmonic emitters. So in this case, the more of a nanoplasmonic emitter you pack in the metal surface, the less thermal radiation you will get. The third case is actually so-called sub-radiance effect. So in this case, you can see this effective number actually is negative. So in this case, the coupling between the nanoplasmonic emitter will enhance the individual emission from the nanoplasmonic structure. So in this case, you can see the total thermal emission will be larger than this uncoupled case. Okay. So basically, we have this three regimes. I also want to mention, Professor Fan's group has a very nice work to discuss the super radiance, sub-radiance thermal emission in 2015.
It's mostly Professor Zhong who gives the answer.
Yeah, that's right. Okay. Yeah. Okay. So we want to really verify these three scaling behaviors. Again, we did a simple experiment. We use e-beam lithography to pattern those nanowires. So here we fix these nanowires with certain geometry. For example, the length here is 2 micron. The width is around 100 nanometers. The thickness is around 30 nanometers. So basically, we just fix the one individual nanoplasmonic structure, but we vary their period in the y direction and period in the x direction. So basically, if we tune these two, we are essentially tune the packing density of this metal surface. When we do this experiment, we actually just fix py, but vary. We fix px, we vary py. And the other one is we fix py, we vary px. As you can see from this measurement, the measured emissivity, certainly we will observe a different radiation heat flux here. So we can also compare with our skew law introduced in the previous slides. You can see here, once we fix the period in the y direction equal to 3.5 micron, but we vary the px. You can see when we reduce the px, that means we pack more nanowires in the metal surface. So we do observe the increase of the emissivity. The other case, we fix the period in the x direction, but we vary the period in the y direction. So you can see similarly, the radiation, the emissivity will increase, but at a certain point, we do observe the emissivity decrease. So this one corresponding to the super radiance effect. So if you pack more nanowires at a certain area, so the radiation will be reduced. But unfortunately, we didn't observe the sub-radiance effect. That's really because our substrate is high loss. It's high index. So we didn't observe the sub-radiance effect. This paper is published in the PL in 2020. If you're interested, you can take a look. So now I want to switch a topic a little bit. For the nanoplasmonic emitters, some of their resonant modes only exist in the near field. For example, we all know the localized surface plasma resonance is only exists at the near field, not in the far field. So the question is, how we can measure those near field resonant modes. Experimentally, this can be very challenging. So here we demonstrate the optical waveguide can be used to extract the near field thermal emission into the far field. So let me tell you how to do it. By converting the evanescent components into the propagating mode in the optical waveguide, the optical waveguide can be planar waveguide or just optical fiber. So in this case, the thermal emission can propagate with a long distance, and then you can measure it remotely. So in this specific example, we did a simulation. We considered the doped ITO as a nanoplasmonic thermal emitter. We couple it with a planar waveguide. We consider two cases. One case is we just put this plasmonic emitter in vacuum. We measure, we calculate the thermal emission at a certain angle, a certain cross section. In the other case, we couple it with a planar waveguide. You can see without the coupling with the waveguide, we get this red curve. But once we couple with waveguide, we can achieve more than 100% enhancement. Okay, so this is because some near field signals can be extracted, become a propagating wave inside this waveguide. At CMU, we also developed an external platform to really demonstrate this effect. So the idea is very simple. Once you have phoners, you can install it with optical fiber. So this one is a quartz tube, right? So we can also pass different gas species, measure it at gas environment. One side we put in the hot room. The other side we can connect it with the spectrometer. And then we can just heat it up and measure the spectral response from our sample. In this experiment, you can see we coated the optical fiber simply with ITO thin film. So this is a doped ITO thin film. So once you heat it up, it will generate the thermal emission. The thermal emission can be coupled into this optical fiber. You can measure it with a long distance. Okay, so think about it. So here I can have a temperature around 1000 Kelvin, but when I do the measurement, at this point, it's only room temperature. Okay, and more importantly, we can measure it with 10 meters away from the hot room. So this slide shows our experimental results. We can measure the spectrum emission at a different temperature. If we integrate the spectrum, we can obtain the total thermal emission we extracted from the ITO thin film. We also did we also did the simulation. So you can compare those two figures. You will see our simulation agree with the experimental results pretty well. But the ITO thin film is pretty simple, right? You just have a thin film. We can also replace. Okay, so let me continue this one. We use ITO thin film as a sensor. So we did the measurement at a different gas environment. For example, here we measure it at a different concentration of hydrogen gas. The hydrogen gas can dope ITO thin film to change their carrier concentration and therefore tune the plasmonic resonance. So in this case, you can see at a different concentration of the hydrogen gas, so we observe a peak shift and also the magnitude change. This result is also consistent with our simulation results. This work can be potentially used as a gas sensing technique. So you can think about when we do the sensing based on this method, we don't need any active light sources. Usually people do the gas sensing, they use lasers, but here we just use thermal radiation. And also you can think about if you have the gas turbine, the exhaust has very high temperature. You can just put the sensor at the exhaust and measure the thermal emission. You can tell the concentration of the gas species you have from the exhaust. So this especially you can do it at high temperature and harsh environment. Okay. To move forward, we can also replace the simple ITO film with a more complex nanorod array, as you can see, from this figure. Our goal is to measure the thermoplasmonic emission from this nanorod array. So the question is how to do it. We have an optical fiber, so which is made from sapphire. We use sapphire because it can tolerate much higher temperature. So here we grow those golden nanorods from one anodic aluminum oxide layer on top of the sapphire fiber. This is as a fabricated nanorod array. So this one is the SEM image for the nanorod after 1 hour annealing at temperature 1100 Kelvin. This one is XRD characterization. You can clearly see before and after annealing at a high temperature, so their crystal structure almost the same. So that means those nanoparticles are pretty stable at this high temperature. As we all know, even the good nanorod has been considered as a very good candidate for localized surface plasma resonance structure. But usually they are not stable at a high temperature. They can only tolerate temperature around 500 degrees C. But here, we can really, anneal it beyond 1000 Kelvin. So that's really because the nanoscale confinement from this anodic aluminum oxide layer. So this is direct simulation results. If we excite 1 nanorod, so this is the electric field, the top view of the electric field, you can, this plasmonic resonance gonna affect the adjacent nanorods. So this figure shows the spectral heat flow. From this figure, you can clearly observe several peaks. The major peak is due to the longitudinal mode of the nanorod. You have a nanorod like this, right? So this is the longitudinal mode. These two minor peaks are due to the hybridization of the transverse mode. Okay. So another question is, can we really observe it, use our, this so-called fiber coupled near-field thermal emission? So we first did a control experiment. So we just measure the bare sapphire fiber. There's nothing over there. You can see we got this yellow curve. And then we put the anodic aluminum oxide layer on top of the sapphire fiber. So we obtain this red curve. So once we grow the good nanorod array inside of this AO layer, so we obtain this blue curve. You can observe around 1 order magnitude enhancement. This experiment also justifies the thermal emission we measured from the fiber is essentially from the good nanorod array. This figure actually is normalized power density. In order to eliminate any artifacts from the optical fiber, so we just use these two, the red and blue curves, normalized to this yellow curve. So you can see for the blue curve, we do observe, clearly observe several peaks. The first peak actually corresponds to the localized surface plasma resonance for the nanorods with aspect ratio 3:1. So this peak actually corresponds to the aspect ratio of nanorod is 4:1. Okay. So this is also the first experiment we can demonstrate the thermally excited localized surface plasma resonance at temperature around 1100 Kelvin. Similarly, we can integrate the spectrum to obtain this total thermal emissive power and compare with the simulation. Again, they agree with each other pretty well. So this paper published in Small last year. So you are interested, you can please take a look. Okay, to summarize my today's talk, we introduced a general theory to really understand the thermal emission from individual nanoplasmonic emitter with arbitrary geometry. We also described a waveguide coupled, thermal emission technique. So in this case, we can really measure the near-field thermal emission with a long distance remotely. We demonstrated 2 experiments. One is ITO thin film, the other one is gold nanorod array. Also based on this technique, we can first time measure the localized surface plasma resonance of gold nanorod at 11 Kelvin. So finally, I want to acknowledge my students and also funding support from NSF and Decca. I'm happy to answer your questions. Thank you.
Thank you, Sheng, for your nice talk. Could you comment a bit the potential limitation you have with this method if you want to generally design metasurface? What kind of limitation you see?
Okay, yeah. Philip, this very nice talk, very nice question. I just want to discuss with you guys. Here, I did all the work based on periodic structure. And also, we work on the simple, nanowires. That's because this is a single mode nano emitter. I think the major limitation is, this one has to be periodic because, when we develop the theory, the Skew law, we use a tight bonding model. We assume it's periodic, it's an infinite array. The other one is, this structure is just a single mode. But certainly, if you have a cross, if you have a, star shape, you can have a degenerate mode. So the physical picture will become more complex. But the question is, if you have a cross, you cannot pack it very densely, right? Because the cross structure will determine what's the maximum period you can have. So in order to observe, for example, this, the super radiance effect, you have to pack it very densely. And then you can observe this reduction of thermal emission.
Thank you very much for the nice talk. I was a bit confused, but probably because I'm not aware of the theory behind it, about what you were calling super radiance and subradiance, since there are a lot of things that are called that way. And from the names that you were giving, I was kind of expecting the other way around.
Yeah,
so
that's right.
Can you probably comment a bit on that?
Thank you. No problem. I think, Professor Fan can talk a little more about that. Really, as I mentioned, Professor Fan and Professor Zhonghu Yu actually is Professor Fan's students. Right now, he's professor at Wisconsin Medicine. He's also personally my good friend. They have this paper. They introduced these two concepts, I believe, at the beginning. So we just follow their derivation, their definition here. And also to mention, you are totally right. When I talk about the super radiance, actually we observe reduction of thermal emission. But when we see the sub radiance, we have the enhanced thermal radiation compared with the uncoupled case. But these two terms actually from, I believe from quantum emission, for example, like you have quantum dot inside the optical cavity, they exactly have the definition for the super radiance and the sub radiance. I think this is just like a comparison. It's just in parallel. You just inherit, their definition and apply it to the thermal emission. Yeah.
Well, maybe I'll make a quick comment and then I'll ask a question. So the point here is that the super radiance enhance the radiation rate. But the thermal emission, as Professor Shen pointed out, depends on the matching of the radiation rate to the intrinsic loss rate. So enhancing the radiation rate may actually lead to a reduction of thermal radiation if you push it away from critical coupling. Just want to make that point. I have a question also. In your probe of the near field spectrum, which is very nice, at the moment, it seems like you can only probe a very limited portion of the wave vector range in the near field. Can you put a grating and so on to really probe deep into the large wave vector regime?
You're totally right. This one, just like what you just mentioned, this one, you can just think about this. We have the evanescent wave from this nanorod. But only a certain wave vector, just like Professor Fan mentioned, can be coupled into the propagating wave inside the fiber, and then we can measure it remotely, right? On the other hand, I also agree with you. If you put some grating over there, probably you can scatter more light, convert them into the propagating mode. And also, I want to mention, another limitation for this work is, so far we only work with optical fiber, but essentially you can also work with a planar waveguide. In that case, you can really use metamaterials, grating. You can do the nanofabrication and make the physics much richer. Yeah.
Just to clarify, this is in terms of fabrication. You buy this with aluminum coating, you anodize them. That's how you do it, or what? this way, this one. You got the core, you got the AAO. How the AAO is made onto the circular.
So this is software. So actually, you can you can code the lumina and on that.
You anodize the lumina.
Anodize it. And then you can do the electroplating to grow nanorods.
Yeah. Now back to Philip's question about the 1,000-time enhancement, right? Did you do a forward scan absorption calculation? What is the structure? Can the structure really reach 1,000 times absorption enhancement?
So actually, what I mentioned 1,000 times actually only is for the entire space. If you, for example, I have I draw a sphere, spherical space just cover the entire nanowire. If I measure the thermal emission at each point, I get around this value.
Yeah. So that's normalized to the say the rod total surface area.
Yes, that's right. That's right.
And the forward absorption calculation gave you that.
That's right. This one, as I mentioned, is this is sub-equivalence. That's why the emission cross section is much larger compared with the physical area.
Okay. Thank you.
A very nice talk. Just for this structure, are there polarization dependence?
You mean this one? Yeah, it is. So certainly it's resonant in this direction.
But that one, the right side, right?
Right side is also polarization dependent. That's a very good question to me.
So your prediction?
When we do the measurement here, so we here even I give you 90%, right? But this is only along this polarization along this way. If you measure this direction, it's almost zero because it's polarized.
Okay, the question now is that how general is this scaling law? Suppose I have a periodical structure of square, rectangle, disk, circle, whatever. How general is that scaling law?
Yeah, so basically, I believe it's very general because when we develop the theory, we only consider the structure periodic. You have a nanoplasmonic emitter. It doesn't matter. You have a nanorod, you have nanowire, you have nanocross, any structure, we don't care. As long as periodic, this theory should be right. Okay, so you can always apply this scaling law to predict the three, cases you have here. And I also want to mention, I showed you guys this curve actually is, we did the calculation in the vacuum. We don't have substrate. Yeah.
Still have time.
Back to this, when you got a PR structure, you calculate the imaginary frequency. Does that mean, does that imaginary frequency also give you the spatial coherence of the emission?
I think mainly give you the loss, for example, the quality factor of your resonance peak and the lifetime of your mode.
What I mean is that let's say you got a CPR structure, right? How many of those rods, their emission correlated? Meaning the coherent emission, does it give you this sort of coherence?
Coherence. We didn't look into the coherence, but in general, I believe this plasmonic structure is coherent. Because you have this is nanowire, it's polarized in one direction. So certainly, what I mean is we treat it like a dipole.
So the question is coherent through the whole domain, or there's a length, there's a spatial region that's related to the imaginary part? That's my question. Is what I'm asking. Basically, let's say if it's a propagating wave, or it's how far extend?
Oh, this one is not a propagating wave. So what I'm talking about here is, for example, we have, let me tell you more details. This is not a propagating wave. We only look at plasmonic mode along this nanorod. So the substrate here is, we have a dielectric. We have a substrate, for example, silicon. We have this mirror, and then we coat with a spacer. And on top of it, we use e-beam lithography to pattern those nanorods. In this case, actually no propagating along this one. So you only have localized surface plasma along this one, but you have the mode overlapping between these two. So this one will give you this effective number of emitters to account for the overlapping. Yeah. We have another work to put this nanorod on top of graphene. So in that case, we have propagating wave. Yeah.
I'll discuss more.
So can you show me actually the slide? You have two figures. On the left, you fixed your PY, you adjust.
Okay. Yeah.
And on the other one is, I just want to.
You're talking about.
Yes, I want to better understand. I want to better understand actually these two figures here. And let's say, okay, on the first one, on the left one, you fixed PY, right? And I just want to consider actually, I mean, for extreme conditions. So if we have a really large, px value, so you see, as the px increase up to 4 and even longer. So I mean, they match. These two curves, just overlap. Just converge into one. Let's imagine there's one extreme case. You have a really large px value. It's totally occupied by gold or your pattern, right? You won't see actually this nanorod.
So what you said is if the periodicity in the x direction is too small, so basically you only see a piece of crystal instead of
the two sparsely separated, right? If your px is really small, so that means actually.
So if you look at the extreme case, that means if you, for example, if px go to 0, so that means if you see this one, if px is 0, that means this nanowire just connect with each other. So you only have a piece of metal.
Thanks.
Quick question.
Hey, Sheng, very nice. I have a question about the previous slide that you had shown.
Okay.
No, the other way.
This one, right? Okay, go ahead.
So you made a point that the curve to the right, if you keep decreasing PY, you have this decrease in emission.
Yes.
But on the left, so if I'm looking at the red curve, it seems like
you
want to go down.
Okay.
But maybe you didn't go low enough. Is that right? Or
so let me explain to you. That's a good point, actually. You can see. So if you look at this one nanowire, right? So we have this dipole mode, but once we pack them, so the interaction in the y direction and x direction will be different, right? Because you have nanowire next to each other, so you have an interaction. You have more area for interaction. But if you do it, the head to tail, so interaction is limited. So that's why, when we do the experiment or do the calculation, so you can actually you can see a small decrease here, over there, but in the experiment we didn't observe it, unfortunately. So so that means probably we need to go even further to make it very, very close, but we didn't do that. So this one, from a theory we can observe it, but from experiment, unfortunately we didn't. Yeah. But this one is very clear. But I have to admit, we only have one data point. I really hope we can do more for this one. Yeah.
Okay, thank you. So let's thank our speaker again.
Okay. Thank you.